So today we are going to start our balanced three-phase circuit analysis. And as this, oh, you guys can't see it. That's probably a little problematic. As we discussed at the end of our lecture on Monday, we're going to start by looking at a YY circuit. So here is our YY circuit of interest, where we have our signal voltage VAN between our A-phase transmission line terminal and our neutral transmission line terminal, which I'll draw in a moment. Here we have the BN. Here we have the CN. And down here on the bottom will be our neutral terminal. So this is B, C, and lowercase n. And because we have we're looking at a YY system, that means we're also going to have a Y connected load. So I'm going to call this guy ZYA. YB. ZYC. And here is our capital N neutral conductor on the load side. All right. We are going to connect our source to our load using a set of transmission lines. So I'm going to call this guy here ZWA. And then our B phase, we're going to have ZWB. And then for our C phase, we're going to have ZWC. And additionally, we are going to consider what happens if we have a neutral conductor with some finite impedance, which I'm just going to call ZN. All right. So this circuit is considered balanced under the following criteria. Right. The first criteria is that the magnitude of our phase voltages at the source are equal, meaning that the magnitude of VAN has to be equal to the magnitude of VBN, has to be equal to the magnitude of VCN. As we discussed in Monday's class, unless our generator is manufactured incorrectly, this is essentially guaranteed. We also need to have the phase separation between the phase voltages at 120 degrees. Since we're dealing specifically with a positive phase sequence system, because that's all we're going to deal with in this class, that means that theta BN has to equal, I don't need that angle, operator there, sorry. Theta BN must be equal to theta AN minus 120 degrees, and theta CN has to be equal to theta AN minus 240 degrees. If we were dealing with a negative, sorry.
What did you label that bottom left side? To the left of the N.
Lowercase n?
N?
Yeah, for the neutral conductor. Yeah, so all of these voltages are measured from the transmission line terminal to the, with respect to the neutral conductor. So for a negative phase sequence, we would have these exact same relationships, except we flip the sign on the phasing. Bradley, what's your question?
Might be jumping the wire, but I wanted to ask, so are these exclusively the voltage phase angles? Will the current phase angles also matter?
We are going to get into that right now. We're just talking about
Okay.
what makes this system balanced first. Then we're going to do some analysis and figure out what the effects of that balancing are. Okay. Yeah, so the magnitude of the voltages have to be equal, and we have to have 120 degrees of phase separation between our voltages. So that's what makes our source a balanced source. To make our transmission line network a balanced network, we need ZWA, ZWB, and ZWC to be equal. So I want to put a very important caveat here. I am intentionally not including my neutral conductor impedance there.
Sorry.
It can have a different value and still balance the system, and we will see why shortly. Okay. In a little bit, we're simply going to represent this as the quantity ZW. So a single quantity that's repeated 3 times as opposed to 3 different quantities all having the same value. So that's what balances our transmission line network. And then lastly, for our load, we are going to need to have our load impedances be of equal value as well, such that ZYA, ZYB, and ZYC are all the same thing. And we'll introduce simply this as ZY in a little bit. So under these specific criteria, we have a balanced 3-phase YY system. Okay. So now we're going to get into our analysis. We are going to analyze this circuit by looking at what are called the line currents, the currents flowing through the transmission lines. And we are going to make some observations regarding the behavior of a balanced system that will all tend to make our analysis more simple in the long run, okay? So I'm going to identify my line currents. So I have this guy, IAA, where I'm using, again, a double subscript notation. So the current is traveling from terminal lowercase a to terminal uppercase a, which is why I have the subscripts in that order. I'm also going to have a line current IBB, a line current ICC, and this guy right here isn't really a traditional line current. We'll see what I mean by that shortly. But we're going to look at how it behaves as well. Since we're going to be applying Kirchhoff's current law, we're going to need to know what that current is. Okay. So these are our 4 currents of interest. And what we are going to do is we are going to assume that our source side neutral node is going to be our reference voltage. So effectively, I'm just setting this nodal voltage arbitrarily with respect to ground. Now, this is actually done in practice a lot. We tie the neutral node to ground. But for this specific example, this is just to give us a reference voltage that we're going to compare everything to for the sake of the math. All right. So what we can do then is if we apply Kirchhoff's current law to the load side neutral, so we're adding all the currents that are flowing into this node on the right-hand side and setting them equal to 0. What we will have, so let's write this down, KCL at capital N. What we will see is that our line currents IAA, IBB, ICC, and INN sum together to make 0. Now what I'm going to do is I'm going to express all of those line currents in terms of the voltage drop across the impedance, the line current C. Okay. So we have a voltage VAN where it starts, and we're going to have a voltage V capital N lowercase n where it ends. So that the voltage drop over the A phase looks like VAN minus V capital N lowercase n divided by ZWA plus ZYA. Sorry, I should be using capital letters for this because that's what I've been doing. Don't want to be confusing. So this represents our line current IAA, and we can repeat this for line currents IBB, ICC, etc. And then the last thing that we're going to do here is I'm going to add in this INN, but I want to talk to you specifically about what I'm going to do, right? What we should see is effectively 0 minus V capital N lowercase n divided by Zn, which is going to be the same as minus V capital N lowercase n over Zn, like so, and set this equal to 0. All right, so we're still just playing around with Kirchhoff's current law, all right? So if our network is balanced, that means ZWA, ZWB, and ZWC are the same quantity. ZYA, ZYB, and ZYC also all represent the same quantity. And so we can say for a balanced network, V capital N lowercase n over Zn is equal to VAN minus VNN over ZW plus ZY plus VBN minus VNN all over ZW plus ZY plus VCN minus VNN all over ZW plus ZY. And so what I'm going to do now is I'm simply going to move all of these VNN terms on the right-hand side of the equal sign to the left-hand side of the equal sign. And so what that's going to do is give me the following relationship. VNN multiplied by 1 over Zn plus 3 over ZW plus ZY is equal to VAN plus VBN plus VCN all divided by ZW ZY. Okay. If our source is balanced, VAN plus VBN plus VCN looks like VAN plus VAN times a factor of 1 angle negative 120 degrees plus VAN times a factor of 1 angle negative 240 degrees. Or another way to put this is VAN multiplied by 1 angle 0 plus 1 angle negative 120 plus 1 angle negative 240. So I'd like for you guys, who've got your calculators out, to just do me a favor here real quick and figure out what this factor that's multiplying VAN comes out to be. Zero, absolutely correct. Okay, so if the sum VAN plus VBN plus VCN for a balanced system is 0, what does that tell us about the voltage drop across the neutral conductor? It has to be 0, right? Because if we have 0 on the right-hand side is equal to some unknown quantity multiplied by a coefficient that is not 0, then that means our unknown quantity has to be 0. So we can say definitively that our neutral voltage, or a better way to put this, the voltage drop across the neutral conductor, VNN, is equal to 0 volts. This is critically important. All right. So from this result, which is only true for a balanced three-phase system, we can observe several things, okay? first, let's look at the current flowing through the neutral conductor. So that's going to be negative V capital N lowercase n over Zn. That has to be 0. So if the voltage drop across the neutral conductor is 0, and the current flowing through the neutral conductor is 0, that's why our neutral conductor is effectively optional. It doesn't do anything. It only serves to carry imbalance in the system, okay? So if we have a balanced system, there is no need whatsoever for us to have a neutral conductor because its impedance does literally nothing, okay? Another very interesting thing about this, notice we have no voltage drop over it, but we also have no current flowing through it, which means effectively our neutral conductor behaves like both a open circuit and a short circuit at the same time in a balanced three-phase system, because it will never do anything. Okay? We are going to use that revelation a little bit later to simplify our three-phase system into something that we can more easily analyze. Okay. Another thing, yes.
Oh, sorry. I just wanted to ask where the current goes.
What do you mean?
So we've got currents flowing in, but none is flowing back out. Because they're like canceling each other out whenever they connect here.
Exactly right. So we'll find that out in just a moment, actually.
So
Yeah. So what you have observed effectively is that the sum, your observation there. Let's frame it that way. Actually, that's a pretty good way to do it. So what Bradley observed is that since our neutral conductor current INN is 0, that means that IAA plus IBB plus ICC must combine together to make 0 as well. Okay. And we'll mathematically prove that here. So our line current IAA, which is expressed as VAN minus VNN over ZWA plus ZYA for a balanced system is just going to be VAN divided by ZW plus ZY. Our line current IBB is going to be VBN minus VNN over ZWB plus ZYB, which is VBN over ZW plus ZY for a balanced system. Or another way that we could think about this would be VAN times one angle negative 120 degrees over ZW plus ZY. Similarly, we could see that our line current through our C conductor will come out to be VAN one angle negative 240 degrees divided by ZW plus ZY. Okay. So what that means is that all of our line currents are balanced as well, meaning they all have the exact same magnitude and they have 120 degrees of phase separation between them. So in a balanced three-phase system, the balance causes the balance from all of our source side being balanced and our load and transmission line being balanced causes all of our line currents to be balanced. Well, if all of our line currents are balanced, all of our phase voltages at the source are balanced, all of our line voltages at the source are balanced, all of our phase currents at the source are balanced, all of our phase currents at the load are balanced. Effectively, if we have a balanced system, everything behaves the property of you have the same magnitude and 120 degrees of phase separation. You don't have to do any work to prove that. That's how it has to work for a balanced system. Meaning that if you can solve for, let's say, the voltage drop over the A phase of the load, the voltage drop over the B phase of the load is the exact same thing as the A phase, just shifted by 120 degrees. We don't have to do a whole bunch of extra work. We can just analyze one portion of the circuit, and understanding that the system is balanced, figure out all the other quantities simply by moving it, phase shifting it by 120 and 240 degrees.
Tie into that neutral node with a multimeter. You're not.
Gonna see nothing. If you have a truly balanced system, Bill.
Some of those things where it's like an ideal thing where we don't really encounter a whole lot of users that always do that, or is there something that's like that?
So it's a little of both, actually. Okay, so let's do a quick aside here. If you are designing a system, and this could be a small system or a large system, your goal should be to make your system behave as balanced as possible. Okay, so I'm going to talk about this from what I do outside of here. Okay, I generate that, or I work on the fabrication of battery energy storage enclosures, which are usually tied to the grid in some way, shape, or form. Right? We use AC power to power the computers and all that kind of stuff. Usually AC power powers the HVAC systems and all that kind of jazz. Okay, so we have an option when we are setting things up. Okay, one of the big options that we have is, are we going to use single phase power for our HVACs, or are we going to use three-phase power for our HVACs? Okay, so in an HVAC unit, which is typically the largest consumption, the largest load that consumes power in our systems, let's say that we are using a three-phase HVAC unit. Okay, well, that means that the compressor, the largest part of that HVAC system, is a three-phase induction motor, which is balanced. However, the blower, a smaller induction motor that's used to force air in or out of the system, is typically a single phase load, so that we inherently have an unbalanced load per building, right? So we have a large three-phase load and then a smaller single phase load that's ancillary to that. So what we'll do is every building, the first building will be connected to the A phase. The second building, the ancillary load will be connected to the B phase. The third building, the ancillary load will be connected to the C phase. So that we effectively rotate them through so that we're balancing things out. As long as we have a multiple of 3 buildings, all of those unbalanced AC systems or HVAC systems look like a balanced load to the transformer that's servicing all of them. Right, so you can design systems where you have repeated elements and place them between specific phases in order to mitigate that unbalance, or at least minimize the amount of unbalance that you have. In a residential area, typically what would happen is that each street will all be connected to a single phase off of your 3-phase transformer. So street A would be connected between the A phase and the neutral, street B would be between the B phase and the neutral, street C would be between the C phase and the neutral, with the hope that power consumption on average will roughly be balanced on the system, right? Now, it might happen, just to make a joke here or whatever, that you might have somebody growing a bunch of pot or something like that. That's how they typically tell. If one string is consuming a lot more power than the others, they can tell that something's kind of suspect somewhere along that string. That's literally that, and then thermal imaging tells you where like grow houses and meth labs and all that kind of good stuff are. It stems from the power industry saying something seems fishy along this street.
What does that imbalance manifest as?
Current in the neutral conductor.
And does that mean there's some kind of loss of power transmission?
No, there's just more power being absorbed on the system. So you're not,
Okay.
the utility is having to provide more power. Yeah, so the utility is having to provide more power. And that unbalance in the system can manifest. So if it were wildly unbalanced, right? So one set of conductors is carrying much more current than the other two. If the conductor isn't rated for that, it can cause physical damage to the conductor in the form of melting, insulation degradation, and things like that. So that's why, typically speaking, we want to design things to be as balanced as possible so that we can use uniform sizing across all of the different iterations of our design, so that we don't have to say, oh, well, this part needs this part needs this. No, we just want it to be cookie cutter image of everything, and then hope that it's as balanced as we can get it. Right.
So what happens whenever like one line fails within the balance system?
It becomes wildly unbalanced. So in, well, I was gonna say in your power lab in your senior year, we used to investigate that exact thing. So if you have a 3-phase motor and you just disconnect one of the phases from the power supply, the motor will still run, but it's no longer a smooth and constant oscillation. It hits and starts, it speeds up and slows down because it's not getting that supply that you would expect. And the exact same thing is going to happen on the system. That's also how they identify where outages occur, because everything looked reasonably balanced and then you get a sudden unbalance. What unbalance tells you the location or the relative location of where something must have happened to unbalance the system. All right, so for a balanced 3-phase YY system, we can actually break it down into 3 equivalent single-phase systems, okay? So this is what we're going to call single-phase equivalent circuits. So in our prior example, we observed that our neutral conductor voltage VNN was 0 and our neutral conductor current INN was also 0. So since there is no voltage drop across our neutral conductor, we can always treat the neutral conductor as if it's a short circuit, even if the neutral conductor doesn't physically exist. Okay. So even if there physically is not a neutral conductor, we can analyze the system as if there were one that happened to be a short circuit. From this, any balanced 3-phase YY network can be subdivided into 3 independent single-phase equivalent circuits. So for our A-phase equivalent circuit, we'll have a source of VAN, our transmission line impedance ZY, excuse me, our transmission line impedance ZW, our load impedance ZY, and then this is capital A terminal, this is lowercase n terminal, this is capital N terminal, and we can treat that connection like a short circuit. And then our B phase is going to be just a copy of that, except that we're going to have a voltage VB in. So lowercase b, capital B, lowercase n, capital N. Connect these bad boys. And similarly, our C phase equivalent circuit is going to look like this. Where here's lowercase c, capital C, lowercase n, and capital N. Okay. And these three circuits behave exactly identically, except that the B phase circuit will lag the A phase circuit by 120 degrees, and the C phase circuit will lag the A phase circuit by 240 degrees. Okay. So we ever really only need to analyze one of them, and then we can just use those lagging relationships to figure out what the phase angle is of everything. Now, one thing that I want to be very clear about here is, I guess, kind of what we can calculate from this specifically, okay? So we could calculate our line current IAA from this pretty easily, just using Ohm's law or something like that. We can calculate our phase voltages across our Y-connected load from this very easily. We can calculate, trying to remember the same colors that I used last class, but I might be messing this up. We can calculate our phase currents, IAN, or lowercase IAN, like so. So we can calculate our phase quantities pretty easily. We can, so phase quantities meaning both the phase voltage and phase current at the load side and at the source side very easily. We can also calculate our line currents very easily. We cannot calculate our line voltages from this. So we're going to have to figure out something to do from there. We can calculate these quantities for the A phase, also for the B and C phases as well. Okay, rather.
So we can't calculate the voltage A uppercase A?
We could, but that would just be the voltage drop across our transmission line, which usually isn't something that we're particularly interested in.
So that's not our line voltage?
No, our line voltage would be V uppercase A to V uppercase B, right? The voltage drop across the transmission line terminals. Right, so our line current and line voltage definitions are a little different from each other, right? Line voltages are measured between transmission line terminals. Line currents are measured as the current flowing through the transmission line itself. Those are two different things, yeah. No problem. All right, so we can get a whole heck of a lot of information from these single phase equivalent circuits, all right? But unfortunately, we are not always guaranteed that we are going to have a YY system. So what we're going to do now is introduce transformations that will allow us to look at any three-phase system, regardless of its actual configuration, as a YY system. So let me go to the next page here. The first thing that we're going to deal with is transformation between sources. All right. So let's first consider a Y connected source. Where this is our voltage VAN, this is our voltage VBN, and this is our voltage VCN. Let's say that VAN is equal to VP, some magnitude for our phase voltage with an angle of 0 degrees. VBN would then be VP with an angle of negative 120 degrees. And VCN would be VP with an angle of negative 240 degrees for a positive phase sequence. So what we're going to do is we're going to figure out what our line voltages are for this source mathematically, right? So for example, if I want to determine the line voltage VAB, what would I need to do? Exactly right. We can apply Kirchhoff's voltage law around this top triangle. And we would find, as Connor suggested, that our voltage VAB would simply be VAN minus VBN, which is the same as VAN times 1 angle 0 degrees minus 1 angle negative 120 degrees, or VAN multiplied by a factor of square root of 3 angle positive 30 degrees. So this is what effectively a conversion factor is that allows us to convert from our phase voltages in a Y connected source to the line voltages in a Y connected source. Okay. Similarly, we could say that VBC is equal to VBN times the square root of 3 angle 30 degrees, and VCA would be equal to VCN multiplied by the square root of 3 angle 30 degrees. So we could use this relationship to make a Y connected source look like a delta connected source, right? Because if we don't have anything connected to our neutral conductor whatsoever, this looks like exactly the same thing from the point of view of the load as a delta connected source. So we can go from Y to delta by multiplying by a factor of square root of 3 angle 30 degrees. How do you think we go the other way around? We divide by that exact same conversion factor. It is that simple, right? So to go from, let me do this in black. So if we have a Y connected source, A, B, C, and N, BAN, BBN, and VCN. And then over here, let's do a delta connected source, A, B, C, where this is VAB, BBC, and VCA. To go this way, let me draw this better. I'm going to draw this like it's a chemical reaction. To go this way, we multiply by √3 angle 30 degrees. To go the opposite direction, we multiply by 1 over the square root of 3 angle negative 30 degrees, which is the exact same thing as dividing by that conversion factor. Okay. So to go from Y to delta, we multiply by, sorry, that should be square root of 3 angle 30. I missed the square root sign. I want to make sure that's clear. So anyway, to go from Y to delta, we multiply by √3 angle 30. To go from delta to Y, we divide by √3 angle 30. That is our conversion factor between our sources. Now let's talk about loads. Okay. And I'm going to start with an unbalanced load. And then we're going to draw conclusions from that that will be applicable specifically to balanced loads. So effectively, what I'm going to teach you guys is the generic delta Y conversion for impedances. And then we're going to apply that to balanced three-phase systems.
-30.
1 over this. So I'm giving you a thing by which to multiply.
In those cases.
Yes.
Just a thing.
So,
Yes.
what is it that we're changing to something else? Is that how to get like BB and C?
Exactly right.
Okay, so we can't get like BB
So we could do VBN to VAB if we wanted to. And so let me explain what I mean by that. We would first do VBN to VBC, and then we would shift it by 120 degrees to give us VAB.
So we just need one thing to start with, and then we can find the others.
Right,
So,
because we know that in a balanced three-phase system, there's 120 degrees of phase separation. So for example, let's do an example to be very, very explicit about this, okay? So let's say that we had VBC was equal to 208 angle 90 degrees volts RMS. And our goal was to figure out what VAN is. So effectively, let's say we're starting with a delta connected source, and we want to know what the A phase of the electrically equivalent Y connected source looks like, okay? So VBN would be 208 angle 90 degrees volts RMS times 1 over the square root of 3 negative 30 degrees. So that's our conversion factor moving from from delta to y. And so what this, so that's going to give us VBC. So that should look like 120 roughly angle 60 degrees volts RMS. And then we know that VAN leads VBN by 120 degrees. So that would be 120 angle 60 degrees volts RMS times 1 angle positive 120 degrees, or 120 angle 180 degrees. So the conversion factors that we've developed are specifically go from the A phase of one source to the A phase of the other source. But because we know that our systems are balanced, once we know what phase we're in, we can shift to any other phase we want.
So we go from phase to phase and then change.
Yeah, so we go from Y to delta or delta to Y, and then we rotate the phase to the one that we need. Okay. All right. Transformation between loads. So let's say that we have a Y connected load. So this is ZYA. Here's ZYB. And here is ZYC. And this is our neutral conductor. And we also have a delta connected load. Let's call this Z delta A. Z delta B. And Z delta C. Okay. What we are about to do is to figure out the rules that will allow us to replace a Y connected load with an electrically equivalent delta connected load and vice versa for an unbalanced case. And then we are going to see what falls out when we constrain these systems to be balanced. Okay. So how we're going to approach that is to effectively look at what the impedance we see is between each terminal pair. So, for example, the impedance ZAB seen between terminals A and B of our Y connected load is what? Exactly right. ZYA plus ZYB. This isn't a trick question or anything like that. What if we're looking at our delta connected load? What is it? I disagree. Why are we neglecting this other path between nodes A and B, right? So it should be Z delta A in parallel with the series combination of Z delta B and Z delta C. Or Z delta A times Z delta C or B plus Z delta C over Z delta A plus, I'm drawing this too large, Z delta B plus Z delta C. Does that make sense? Why we have to include that other bit as well? Obviously, Z delta A is directly between terminals A and B. We also have this other path that current could take that we need to take into account. Okay. So if we equate these two expressions for ZAB, what we'll find is that we're going to get one equation. So let's just call this number one. ZYA plus ZYB is equal to Z delta A times Z delta B plus Z delta C over Z delta A plus Z delta B plus Z delta C. And if we do the exact same thing between terminals B and C, which I should put a C down here, we're going to get ZYB plus ZYC is equal to Z delta B times Z delta A plus Z delta C over Z delta A plus Z delta B plus Z delta C. And finally, our third equation, yields ZYC plus ZYA is equal to Z delta C times Z delta A plus Z delta B, all divided by Z delta A plus Z delta B plus Z delta C. The reason why I've organized it as such is we have developed three equations, and effectively we can treat this as a three equation, three unknown system. Meaning that if we know what our Y connected impedances are, we can solve for our delta connected impedances. Or if we know what our delta connected impedances are, we can solve for our Y connected impedances. So what we will find is that Z delta A is equal to ZYA times ZYB plus ZYB times ZYC plus ZYC times ZYA all over ZYA. So that's how to find Z delta A in terms of our Y connected impedance. And we'll do the same thing for Z delta B and Z delta Z here. So our numerator is going to be the same each time. And our denominator is going to be the phase that we're interested in. All right. So this is what our unbalanced representation looks like. Let's talk about what happens when things are balanced, right? So for a balanced system, we should expect that Z delta A is equal to Z delta B is equal to Z delta C, where we know that ZYA is equal to ZYB is equal to ZYC. So effectively, if all of our Y terms are the same, we have ZY squared plus ZY squared plus ZY squared in our numerator. So 3ZY squared divided by ZY gives us 3ZY. So our delta connected balance load is simply 3 times the impedance of our balanced Y load. So the impedance per phase looks 3 times as large. Now, developing the other set of equations. ZYA is going to look like Z delta A, Z delta C over Z delta A plus Z delta B plus Z delta C. ZYB is going to look like Z delta A, Z delta B over that same denominator. And because I'm running out of room here, I'm going to tuck this one in the middle. ZYC would be Z delta B, Z delta C over that same denominator. And when our system is balanced, we can see that ZY will be, so this is going to be Z delta squared over 3Z delta, or simply ZY is equal to 1/3 delta. So our Y connected equivalent impedance is just per phase. It's just our delta connected impedance per phase divided by 3. So this is how we're going to be able to transform any balanced three-phase system into a YY system, right? And actually, we've developed the rules for making any three-phase system, regardless of whether or not it's balanced, actually look like a YY system as well. So that if we had to, we could go back to the techniques that we did at the very beginning of class where we analyze that system as if it were unbalanced and solve for all of those quantities too. Probably won't actually have time to do that in this class. I've never managed to have time to cover unbalanced systems, but if we wanted to, that's how we would approach it. All right, so I think this is a good stopping point for me today because we only have about 6 minutes or 7 minutes left of class anyway. Not enough time to do an example problem. So what we are going to focus on Friday is applying these transformations and actually getting to the analysis part of this. Okay, so we're just going to work example problems that will be very similar to homeworks that I'm going to put up this afternoon on this material. And then on, let's see, that'll be Friday. On Monday, we'll do three-phase power analysis. And then if we have anything left over, we'll take care of that on the next Wednesday. Because our final is supposed to be Friday of next week, right? Literally the last day. Okay. Catherine, are you okay with that? You give me a look.
Sorry, no, I'm good.
Okay.
I'm just thinking.
Yeah, I'm willing to work with you if we need.
No,
Bradley, what's up?
So just three quick questions. What will homework due dates, take home test for test 4 and our project 3 look like?
So I'm going to try to put up your take-home test for exam number 4 up Friday. It'll be due next Friday. You probably won't be able to do all of it over the weekend, but you should be able to do roughly half of it over the weekend, just understanding the analysis, the circuit analysis portion without knowing the power analysis portion. For the project, I may just not do it because that'll be less crap for me to do and less crap for you guys to do. Regarding the homeworks, I'm very likely going to put up the 3 remaining homeworks that I have left for this material, and they'll all just be due Friday at midnight. Now, I do want to say something here, okay? You're going to have your take-home exam, your homework, whatever number we're up to, and then that +1, and then that +2, because there's going to be 3 homeworks sets for this material. All of those are going to be due effectively at the same time. I'm going to put the date, the due date as Friday at 5 p.m. because that is the end of the quarter. If you turn it into me over the weekend, I'm good. No late penalty or anything like that, but I can't make anything due after the quarter is over. So I will magnanimously accept it all the way up into Sunday at midnight, but it's due on Friday at 5, if you're catching what I'm throwing. Okay. All right. Does any of that sound unreasonable? Effectively, so let's see. Friday is the 20th. So you'll have until midnight on the 22nd to get all of that crap finished. And I'm going to give it to you all, hopefully today. Yeah. All right. So that's where my head is at. Does anybody, does that sound wildly unreasonable?
These balance systems, do they function on a macro scale too, where like you've got 3 streets and then I've got 3 groups of those 3 streets?
Absolutely. Yeah. 100%. Yeah.
I was just wondering like how they kind of cascade the troubleshooting, and that would be a good way to do it.
Yes, no, so very much so. So we're going to talk about, we'll probably work one problem on Friday where instead of just having a source connected to a single load, we'll have a source connected to multiple loads. That could be representative of the load seen from one street. You know, one load is the load from one street, one load is the load from the next street and all that kind of stuff. So yeah, it absolutely cascades. Like if it didn't, the electricity grid couldn't exist.
Okay, yeah.
I wanted to ask what elective classes have to do with most of this stuff and with the power transmission.
The power classes.
Power classes?
Yes, so there is a full-on power sequence in your senior year. ELEN 484, which is all about rotating electric machine electronics, is the prereq for power systems, which is one of the senior options classes. And then in the spring, there is usually a 3rd power elective that could be power systems design, could be motor control, could be advanced power systems analysis, just whatever Dr. Patari wants to teach or whatever you guys talk him into teaching is what that 3rd power class is. But
Is that the IC class?
no,
So
All of those are EE classes, yeah.
So the power 1 and 2 are those ICT or those?
We have a power 1 and 2 class. If you are pursuing an EE degree, the only potential ICT class you would ever take would be on PLCs because we don't do that.
Okay, because I have a friend in ICT and he's telling me about the classes and I don't know if those are the same, the different ones you're talking about.
They're very much different than ours.
Okay.
Ours are from a much higher level, like of math analysis, and you're expected to have this calculus-based background that they largely are not.
Okay.
My buddy William teaches those classes. This is his first time going at it, so who knows how they're doing.
The EE or the ICT?
The ICT. Dr. Batari is at this point solely responsible for teaching the electrical engineering power courses because that's where his research is, and so that's his area of expertise. Yep.
Really appreciate it.
Yep. Anything else?
I apologize for showing up late. I've been fighting falling asleep for the last 30 minutes of class here today.
Oh, yeah, you're good. Didn't even realize. Like, I knew that you came in late and you sat way in the back, but I can't see well enough to tell that you were falling asleep, so it doesn't matter. Anything else? All right, see you guys on Friday.